Okay, thank you. Thanks, Chair, and hello, Wang. I'm Huan Wang from Tsinghua University. I'm very delighted to be here and share our research in computer vision and its application in our indoor environment. So my contents will be listed here. It may contains two major parts for the application of computer vision in two aspects, and finally the conclusion. Firstly, let's come to the background. Due to the pandemic, we have mentioned a lot about the ventilation. It is very important for both for health and for our productivity. So, especially in these days, it is very important for us to prevent from the virus, and also it is an important thing for us to have a better ventilation in an energy efficient way, because it is normally very expensive and not available for all the year round. And for better ventilation, the first question is about how to measure it. It's the air is invisible and very difficult to measure because it is highly turbulent in our indoor environment. Its speed can change very dramatically, and also its direction is very difficult to measure. Normally, we have smoke visualizations as presented by previous researchers. It's very easy to understand, but very difficult to get quantitative results. For invasive instruments, normally we may use a hot wire anemometer or sonic anemometers. This kind of instruments must be put into the floor to get the data. So it may okay for high-speed airflows, but in our indoor environment, the speed can be very low at some time and some place. So it could become an obstacle for the airflow and may disturb this flow phenomenon, especially for the airflow around people, which is not that strong enough. For non-instrument intrusive instruments, mainly based on the image, it's the problem here is mainly about the limited measurement space, like PIV and the PTV. It's not large enough. It normally within 1 meter in range. So it's not. But for our room scale, it's several meters wide. So it's normally it's not that large enough to cover the space. So a non-intrusive measurement system for with large measurement range for airflow is very desperately needed for further study. So this is one question, and the other is here. The actual scenario is always changes because, for example, in this room, we take 3 pictures in one day, and we can see the dramatic changes. And also for different people, their preferred temperature or environment could be different dramatically. And in large space buildings, the occupant zone is totally different from what we used in regular buildings. And as analyzed, only 10% of the total running time it is running within our design conditions. So it is very difficult to find and operate the system, ventilation system or HVAC system, according to the real scenario. So here are the 2 problems here, how we measure the airflow and where is the occupancy. These are the 2 major 2 difficulties for the ventilations in nowadays studies. And when we're doing this kind of issues, we move our eyes to the computer vision, which has bring us new creators like autonomous driving and motion sensoring. With these things can change a lot of our daily life and our understanding of the world. So let's come to its application in airflow measurements. The airflow is transparent and very difficult to capture, so we use we use a helium-filled bubble, which is very small, but can reflect the light around them very well for us to capture the movement of the air. And but the major problem for this system is here the bubble looks just the same between each other. They're all round and they're very difficult to trace. So we build a color sequence lighting system to which we can change the light of the measurement zone, and therefore we change the appearance of the bubble. So we use a longer exposure time. We can capture the entire trajectory of the bubble with some red, green, and blue dots on it. As we change from red to green to blue, we capture the entire trajectory and its direction. So like in this picture, we combined the instant instant image from PTV and long streaks from particle streak PSV. We got this kind of combined images, which we change the light from red to green to blue. So we got a displacement within the time, and also we got the flow direction of the bubble. So with this innovative image taking system scheme, we build a CSPSV, and the system is built up in our in laboratory with a measurement of 4 meter wide, 2.5 height, and 0.8 in depth, which is the world largest laboratory in this kind of type, and it can get very good accuracy, especially when the flow is of a very low speed, because these bubbles can flow very well with the air. So with this system, we can capture and measure more detailed air flows in the space, even for very difficult to measure or complicated flows like this in a ceiling fan is propelling the air through the entire space at a very high speed and get around in the room. So with our system, we can capture three-dimensional and three-component vectors with million vectors. So we can use it to cut at a different height and capture the flow character of this kind of a certain application, and we can also calculate the average speed and viscosities to see how it moves and what is the flow character about. So this is for one application, and we use it for even more applications. Like in this picture, we use a mannequin to exhale bubbles, and we can measure the spread speed and also the spread range of the exhalations from the patient or virus. Some kind of estimation to evaluate the danger for infection, and also we capture the exhalation from people, just as previous researchers reported, the lockup phenomenon in displacement ventilation, and also we use it to measure the mixing ventilation at the room scale. So with this system, we also use it in a field test in a large stadium to measure what the airflow really looks like in a even larger space and in a real project to give conclusion and give reference for the operation in just ice cubic, which will be will also be Olympic Game Stadium in 2022. And so here is our research system, our research in airflow measurement system. And another question is here, where is the occupancy and what about the scenario recognition? So here's a second part. We use multiple cameras to get in the room and use triangulations, which is also can be called as multi-wheel geometry to capture the people from different wheels, and we can use the collaboration data to get a data fusion to get and calculate the exact 3D position of the people's left, right, shoulder and the neck. So we have 3 points here, and we use this apply this system in our department. Here is an example of with less people. We can see we can demonstrate their direction and position of these people, and even for people with different gestures, we can recognize that. So it's for dance for less people. When people more people are coming around and have a meeting, we can also see here the system can tell us even more information about the gestures we may not cannot easily be found, and so find some discussions between these two people can easily demonstrated in the system. So here is just the people's location, and with the even developer of the camera, we can capture the entire space in 3D point cloud, like in this video, and this is real-time capture. You can hit there, but we use 4 cameras and merge them together to get the entire space within the room at 5 frames per second. So this kind of data can tell us what is furniture looks like and other settings of the room. With this kind of information, we can further improve our human positioning system or occupants positioning system, and with furniture and other equipments together captured from this system, we can mark the people with red white dots, and also we have all the settings and furnitures inside in this room. So this kind of information can help us to operate our ventilation system or HVAC system more directly to the people and to the different scenarios really happening in the room. So here are just 2 examples we have conducted in these years, and we can find that computer vision really can greatly help our indoor environment. Our CSPSV provides an important research tool for the indoor airflow measurement, and also the occupants positioning system and the scene recognition system can help us to better understand what is happening and what is the real status of the room. So the information captured by CV and can help us to create a healthy, comfortable, demand-oriented, and energy-efficient indoor environment. Thank you.
Thank you very much, Dr. Wang. I think you have sort of similar research field with other panelists. So I also hope that maybe at the end of our session, we'll have the panel discussion. You could ask each other about the research questions and the technology, what's the differences, because actually I'm from the urban planning field. I'm trying to know more about how this kind of technology, what's the difference, what's the innovation part, and how it may applied to the urban context. Because
thank you.
More like all right, thank you. We will have our last speaker, and then I would invite all our speakers coming back. Okay, we will have the last speaker, Dr. Zhonghua.